There is a structure on the Giza Plateau in Egypt that has been standing for approximately 4,500 years, and the more precisely modern instruments measure it, the more difficult it becomes to explain how it was built using the tools that the historical record says were available at the time of its construction. This is not a fringe observation made by people who want to believe something extraordinary. It is a mainstream engineering problem that has quietly troubled researchers for generations, one that the popular account of pyramid construction consistently understates and that recent high-resolution analysis has brought into sharper focus than ever before. The Great Pyramid of Khufu is not mysterious because it is large. Human beings have built larger things. It is not mysterious because it is old, though its age is genuinely staggering. It is mysterious because of what the measurements say about how it was made, and because those measurements keep producing results that the conventional story struggles to accommodate without a level of special pleading that honest investigators find increasingly uncomfortable. The new evidence that has emerged from comprehensive three-dimensional modeling of the pyramid, assembled from laser survey data, geological scans, astronomical records, and the precise dimensions of the surviving internal and external features, does not contradict the basic historical account. It does something more subtle and in some ways more troubling. It accepts the basic account and then demonstrates that the basic account, even taken at its most generous, does not explain the specific and measurable qualities of what was actually built. The labor is real. The organization is real. The workforce is real. What remains unexplained is the precision, and the precision is the thing that the new measurements keep illuminating in ways that push the conversation into genuinely uncharted territory. To understand why the precision is the problem rather than the scale, you need to first give the conventional account the fair hearing it deserves, because it is a serious account built on serious evidence that should not be casually dismissed. Around 2,560 years before the Common Era, during the reign of the pharaoh Khufu in Egypt's 4th dynasty, an enormous building project was organized on the limestone plateau on the western bank of the Nile near the city we now call Cairo. The project involved quarrying millions of blocks of limestone from the plateau itself and from sites nearby, transporting finer casing stones from quarries downriver by barge, and then moving all of this material across the desert and raising it, course by course, over a period of approximately 20 years, to produce a monument covering more than 13 acres of ground and reaching, at its completion, a height of nearly 147 meters. The workforce that did this was not, as older popular accounts suggested, composed of slaves driven by whips under the desert sun. That image has been largely replaced by a more accurate and considerably more interesting picture drawn from actual archaeological evidence. Excavations at Giza have revealed the workers' village, the actual physical settlement where the people who built the pyramid lived while they were doing it. There were bakeries capable of producing bread at industrial scale. There were breweries. There were medical facilities where workers received treatment, evidenced by skeletal remains showing healed fractures of the kind you would expect from heavy construction work. There are administrative records, including one of the oldest written documents ever discovered anywhere in the world, a papyrus written by an official named Mirror who was overseeing the transport of stone to the Giza site and who recorded the daily logistics of that work with the matter-of-fact thoroughness of a competent administrator doing his job. Inside the pyramid itself, painted in red ochre on blocks that were never intended to be seen by anyone after construction, are the names of the work gangs who placed them, crews who called themselves things like the Friends of Khufu and the Drunkards of Menkaure, real human beings who took pride in what they were doing and signed their names to it in the dark. This is not mythology. This is documented history, and the new research that has unsettled so many assumptions about the pyramid emphatically does not challenge it. Human beings built the Great Pyramid of Khufu. The evidence for that is overwhelming and specific in ways that make alternative origins unnecessary and implausible. What the new evidence challenges is not who built it but how certain aspects of it were achieved with such extraordinary and apparently unnecessary precision. Begin with the foundation, because the foundation is where the problem first becomes quantitatively visible. The pyramid stands on a base measuring approximately 230 meters on each side. That is a footprint covering an area large enough to contain several city blocks. Across that entire footprint, the deviation from perfect level, the difference between the highest and lowest points of the foundation platform, is approximately 2 centimeters. 2 centimeters across 230 meters. When you calculate that as a percentage, you arrive at a flatness ratio of roughly 0.009%. That is not just impressive. It is, by the standards of modern construction engineering, extraordinary. Contemporary engineers building large-scale foundations with laser levels, optical theodolites, and precision surveying equipment routinely work to tolerances considerably looser than this, because for most structural purposes, tolerances considerably looser than this are entirely sufficient. The pyramid's foundation exceeds what modern construction typically demands of itself. Now consider what tools are attributed to the Egyptian builders who achieved this. Wooden squares. Plumb lines weighted with stone. Shallow trenches cut around the perimeter of the building site and filled with water, whose surface, being naturally level, provided a reference datum against which the surrounding stone could be compared and adjusted. These are genuinely clever tools, and they demonstrate that the builders understood the principles of leveling clearly. But they are also tools with inherent limitations. Water in an open trench is affected by wind. It is affected by evaporation, which happens rapidly in desert conditions and can be uneven across a large area. The trench itself must be cut with precision to be useful as a leveling reference. And the entire operation must be repeated and verified thousands of times across a 230-meter span, by workers who are also doing everything else that building a pyramid requires, over a period of years during which the seasons change and the light changes and the conditions under which measurements are taken are never perfectly consistent. The three-dimensional modeling analysis examined this problem statistically, asking what the probability was of achieving the observed flatness using the documented tools under realistic working conditions. The answer was not that it was impossible. The analysis was too careful for that kind of overstatement. The answer was that the odds were considerably worse than comfortable, that the documented tools could in principle achieve this result but would be expected to produce it only rarely, and that the consistency with which the result was achieved across all four sides of the foundation simultaneously made the comfortable explanation less satisfying than the numbers required it to be. Then the analysis turned to orientation, and the numbers became even more challenging. The four faces of the Great Pyramid are aligned to the four cardinal directions with an accuracy of approximately 3 arc-minutes. An arc-minute is 1/60th of a single degree. 3 arc-minutes is therefore 1/20th of a single degree, a deviation so small that it is invisible to the unaided eye at any reasonable distance, detectable only with precision instruments. Modern theodolites, optical survey equipment calibrated and maintained to professional standards, routinely work to tolerances of a few arc-minutes. The Great Pyramid's alignment to true geographic north is within the working tolerance of a modern precision surveying instrument. The critical distinction here is between magnetic north and geographic north. A compass points to magnetic north, which varies by location and changes over time as the magnetic field of the Earth shifts. Geographic north, true north, is fixed by the rotational axis of the planet itself and does not change. Aligning a building to true north with an accuracy of 3 arc-minutes cannot be done with a compass. It requires astronomical observation, watching the stars rotate around the celestial pole across the night sky and identifying the precise point around which that rotation occurs. This is sophisticated astronomy, not elementary observation, and it must be combined with sophisticated surveying to transfer the astronomical reference to a line on the ground and then hold that line with the observed accuracy across a 230-meter span. The analysis posed a question that the conventional account rarely asks directly. Why? Not how, but why. A tomb does not require alignment to true north within 3 arc-minutes. A monument to royal power does not require it. A religious structure oriented approximately toward the sun or roughly toward the cardinal directions for ceremonial purposes does not require it. The accuracy achieved at Giza far exceeds any functional or ceremonial requirement that historians have been able to identify. It demanded an enormous additional investment of effort and skill beyond what any practical or symbolic purpose could justify, and the investment was made anyway, consistently and across all four sides, in ways that the documentation of the building's construction does not explain. The mathematical relationships encoded in the pyramid's proportions represent the next and most conceptually challenging layer of the problem. When the model computed the ratio of the pyramid's perimeter to its height, the result was not a round number or an arbitrary value. It was approximately 2 times pi, the mathematical constant that describes the relationship between a circle's circumference and its diameter, accurate to within a fraction of a single percent. In a structure made entirely of flat surfaces and straight lines, the fundamental constant of circular geometry appears in the basic proportional relationship between the horizontal and vertical dimensions. There is a reasonable conventional explanation for this, and it deserves to be stated fairly. The Egyptian builders used a unit of measurement called the royal cubit and a slope measuring system called the sect, which expressed a pyramid face's angle as a ratio of horizontal displacement to vertical rise in units of palms and fingers. A particular sect value that was practical and appealing to the builders would naturally produce a height-to-perimeter ratio that approximated 2 pi, not because anyone was thinking about circles but because the arithmetic of the measurement system generated that result as an unintended consequence. Pi, in this reading, was not encoded deliberately. It arrived by accident through the back door of a practical measurement convention. The model accepted this explanation as possible. What it could not dismiss as easily was the margin of fit. If pi were an accidental byproduct of practical measurement conventions, you would expect the fit to be approximate, the kind of rough correspondence that emerges when two things happen to be vaguely similar without being carefully matched. The fit in the Great Pyramid is not rough. It is extremely close enough that expressing it as accidental requires accepting that the accident was unusually precise, that the particular sect the builders chose produced a pi approximation considerably tighter than most sect values would generate. Possible, but progressively less comfortable the more closely the numbers are examined. The second mathematical constant found in the pyramid's proportions is the one the analysis found genuinely difficult to account for through any conventional mechanism. Phi, the golden ratio, approximately 1.618, is a proportion that appears throughout natural systems, in the spiral growth of shells, the branching patterns of plants, the proportional relationships that human beings across cultures consistently find aesthetically pleasing. Unlike pi, which can appear accidentally in any system involving circular measurement, phi cannot arrive through a random or unconscious process. It must be understood as a specific numerical relationship before it can be incorporated into a design. You cannot stumble into phi. You have to know it. The three-dimensional modeling found phi not in one place in the Great Pyramid's geometry but in approximately 7 independent locations, in the relationship between height and base dimensions, in the angle of the faces, in the proportional relationships between the internal chambers and the passages connecting them, in multiple distinct and geometrically independent features of the structure. 7 appearances of a number that cannot arrive accidentally, in a building constructed more than 2,000 years before phi was formally described by any mathematical tradition whose records have survived. The Greek mathematicians who first wrote down a formal description of the golden ratio were doing their work roughly 2,000 years after the Great Pyramid was completed. The analysis posed this as a logical problem with a small number of possible resolutions. Either phi appeared in 7 independent locations of the pyramid by a coincidence of geometric relationships that nobody has yet identified, which becomes statistically implausible with each additional appearance, or the builders understood phi and used it deliberately, which requires that sophisticated mathematical knowledge existed and was applied at a period considerably earlier than the written record of mathematical development accounts for. Both conclusions are uncomfortable. The first requires accepting coincidences that strain the mathematics of coincidence. The second requires revising the accepted timeline of human mathematical achievement. The most extraordinary numerical relationship in the entire analysis connects the pyramid not to abstract mathematics but to the physical dimensions of the Earth itself. When the height of the Great Pyramid at its original dimensions is multiplied by a factor of 43,200, the result matches the polar radius of the Earth, the distance from the center of the planet to the geographic pole, to within a small fraction of a percent. When the perimeter of the pyramid's base is multiplied by the same factor of 43,200, the result matches the equatorial circumference of the Earth, the distance around the planet at its widest point, to comparable accuracy. The same multiplier connects two different dimensions of the building to two different dimensions of the planet simultaneously. The analysis examined whether this multiplier was arbitrary, whether it was the kind of number that could be chosen after the fact from the infinite range of available numbers to make any two measurements appear related. It was not. 43,200 is the number of seconds in 12 hours, in half of one rotation of the Earth on its axis. The bridge between the building and the planet is built from the planet's own rotation rate. The subject of the encoding and the measuring instrument used to encode it are the same object. What makes this relationship even more difficult to dismiss as coincidence is the distinction it captures between the Earth's two relevant dimensions. The polar radius and the equatorial circumference differ from each other because the Earth is not a perfect sphere. Rotation causes the planet to bulge outward at the equator and flatten slightly at the poles, making the equatorial circumference measurably larger than the distance over the poles would suggest if the Earth were perfectly round. This distinction, the precise degree to which the Earth is an oblate spheroid rather than a true sphere, was not confirmed with scientific accuracy until the era of space-based measurement. The Earth's exact shape was an open question for most of recorded human history. And yet the pyramid encodes both values, polar and equatorial, simultaneously and accurately. The Sphinx, sitting a few hundred meters southeast of the pyramid and considered by most conventional accounts to be approximately contemporaneous with it, presents a separate and equally challenging anomaly that the modeling study also examined. The Sphinx does not stand on open ground. It occupies a pit cut down into the bedrock of the plateau, and the walls of that pit show a pattern of erosion that geologists who have studied it describe as inconsistent with wind erosion in a desert environment. The channels in the enclosure walls are rounded and run vertically, carved from the top downward in the smooth undulating pattern that water produces when it flows continuously down a vertical face over an extended period. Wind erosion produces a different signature, scouring horizontally along the direction of sand travel, attacking soft layers while leaving harder ones projecting outward. The weathering pattern on the Sphinx enclosure suggests sustained rainfall erosion rather than Aeolian desert erosion. The problem is that the Giza Plateau has been hyper-arid for longer than the conventional dating of the Sphinx would suggest. The kind of sustained heavy rainfall required to produce the observed weathering pattern corresponds to a much earlier climatic period, the Green Sahara era, when significantly wetter conditions prevailed across North Africa, a period that ended thousands of years before the accepted construction date of the Sphinx. If the weathering was caused by rain, and the geological signature strongly suggests it was, then the structure being weathered was already standing when the rains fell, pushing its origin back considerably further than the textbooks currently place it. None of this evidence leads to a single clean conclusion. The modeling analysis was explicit about this, listing several possible frameworks for understanding what the evidence reveals without committing to any one of them as definitively correct. One possibility is that the builders of the Fourth Dynasty possessed mathematical and surveying knowledge considerably more sophisticated than the surviving record of Egyptian intellectual history would suggest, knowledge that was not transmitted in the written form we would need to confirm its existence, and that may have been lost after the Pyramid Age without leaving recoverable traces. Another is that the knowledge encoded in the pyramid was inherited from an older tradition, a predecessor culture whose own achievements preceded the dynasties and whose understanding of mathematics and planetary dimensions was passed to the builders of Giza in a form they could apply without necessarily fully comprehending its origins. A third possibility, consistent with geological evidence from other contexts, is that sophisticated knowledge existed in the pre-agricultural world before the climate catastrophes at the end of the last ice age disrupted and dispersed whatever civilizations had developed it. What the new evidence definitively establishes is that the conventional account is insufficient. Not wrong in its particulars, not fabricated, not ignorant of the real history, but insufficient. It explains the labor. It explains the organization. It explains the supply chains and the workforce management and the political authority that could sustain a project of this scale across 2 decades. What it cannot explain is the mathematical knowledge that appears in the building's proportions encoded with a precision and completeness that the conventional timeline of human intellectual development does not account for. The pyramid was built by human beings. The evidence for that is beyond serious question. How those human beings knew what they knew, where that knowledge came from, and what happened to it afterward, Those are questions that the new measurements have made more urgent and more genuinely open than the comfortable version of history has generally acknowledged. The Great Pyramid has been standing in the desert for 4,500 years, patiently encoding in stone a set of measurements and proportions and astronomical alignments that nobody appears to have fully decoded until instruments precise enough to read them were developed. It waited. Whatever it contains, whatever knowledge was pressed into its limestone courses by whoever understood it well enough to do so, it has been waiting in the desert for someone to ask the right questions with sufficiently precise instruments. The new evidence suggests we are finally beginning to ask them. What the answers will require us to revise about our understanding of the past remains, for the moment, genuinely and fascinatingly unknown.